So, yeah, before we start this chapter, okay, one thing to remind you is that, I mean, the second homework is due the day after tomorrow, right? Okay, this Friday. Okay, the reason I said the due date to be Friday is because starting Friday is a spring break, right? So I don't want you guys to worry about the class during the spring break, and I didn't know the spring break at our school is a week long, right? Until, I mean, the next week is the whole next week is off, right? Is that correct? Or just I mean, does that include Friday or not? I'm not sure. No. So Friday has class. Okay. Yeah. But anyway, we don't have class on Friday. Yeah. So next week I mean, we don't have class, obviously. Yeah. So, well, so I don't want you to wait I mean for too long. I mean, hopefully you can have you can just submit the homework too and enjoy your holiday. Okay. Okay. Now we are in the position to talk about modeling with linear regression. Okay. If you ask me what statistical model is the most commonly used one, okay, I will tell you it's a linear regression. But a linear regression is not just one model. It has several models. I mean, they are all under the umbrella of the linear regression. So as you can see, it's building block for many other models, such as multiple linear regression, logistic regression, which sometimes is also called logistic linear regression, and ANOVA, ANCOVA. Okay, ANOVA, I'm not sure. I mean, ANOVA and ANCOVA, I'm not sure if we will be able to cover that in this class. But you can see that. I mean, this chapter we are going to talk about simple linear regression, robust linear regression, hierarchical linear regression, polynomial regression, multiple linear regression, interaction, the variable variance. Okay, all this in this chapter. So we are going to talk about a lot of material. Okay. Actually, in terms of model, okay, I believe the last chapter and this chapter as well as the next one. The next one I think is called a generalized linear model, okay, which is built obviously on top of linear model. Okay, it's these three chapters basically cover. I cannot say 90%, but I would say it's the majority of model Bayesian data analysis modeling. Okay, majority of that. Okay, so yeah, I mean, let's try to finish up this chapter, and hopefully maybe we spend some time on the sampling technique, and come back to finish a generalized linear model. Okay. So anyway, so let's continue. So many problems, okay, in our domain, okay, or business area, okay, it looks like you have a variable x and want to predict a variable y, okay. So, I mean, these variables are normally paired, like x1, y1, x2, y2, and so on. Okay, so this is I mean, in simplest scenario, okay, we call this a simple linear regression. Okay, in simple linear regression, x and y are unidimensional, continuous, random variable. Okay, So, so when we call them random variables, we implicitly assume like we are using statistical model to solve this. Okay, because like if you are talking about like for example, like the simple like a matrix like a solution, okay, then we normally treat them just as variables, okay. But anyway, okay, so we call Y variables the dependent or dependent variable, okay, predictive variable or outcome variable. Right? The X as like independent variable, predictor, or input variable. Okay, so these are just the term. But to be honest, like in machine learning, as I will later mention, okay, we don't use the term variable. We normally use the term feature. Okay, but basically we are referring to the same thing. Okay, so when X is a matrix, okay, then we are talking about multiple linear regression. Okay, so linear regression model, okay, can be used in situations like this, like a model the relationship between factors such as rain, soil salinity, okay, salinity, okay, and so obviously rain, the soil salinity has certain, some very simple relation, okay, and the presence or absence of fertilizer in crop productivity, okay, so normally, if you put more fertilizer, okay, when you plant, in a farm, okay, you will generate more, crops. That's common knowledge. Okay, that's why we have to, the farmer have to purchase fertilizer, right? So, answer questions such as, is the relationship linear? We know they have relationship, but their relationship may be linear, may not be linear. Okay, so if it's linear or not, then how strong is this relationship? Okay, which factors have the strongest effect? Okay, because there may be several factors that impact the result. Why? Remember, like X can be more than one. Okay, we're not saying just X is, we have only one X value. We may have like multiple factors. So which one has the strongest effect? So all this can be answered by linear regression model. Same thing, okay, the other part, find the relationship between average chocolate consumption by country and the number of Nobel laureates in that country. So they understand why this relationship could be spurious. So this relationship, you will find that, okay, the average chocolate consumption and the number of Nobel laureates, okay, if you look at the statistical result, okay, and you try to model it, you will find that there are relations, okay, there are certain relationship, okay, interestingly, okay, but obviously, if you use your common sense, you will see that it doesn't make sense, right? It shouldn't be like that, right? Okay, so we will also explain like why this relationship is spurious. It's not plausible. Okay. One possible explanation is that, okay, yeah, the chocolate consumption actually has something to do with like the what should I say, like the average income. The more income a country has, like maybe the more chocolate consumption this country has, right? And the more income, the average income, in a country, the more likely that country is going to produce Nobel laureates. Something like that. Okay, who knows? But anyway, this relationship is not that plausible anyway. So anyway, okay, we are going to also look at predict the gas bill, okay, of your house by using the sun radiation from the local weather report. Okay, so this is also a very interesting one. Okay, because gas bill, okay, has something to do with sun radiation. You will see there are certain correlations. Okay, so how accurate is this prediction? Okay. Once we build a model, we'll see it can, it can be used to predict the result. And we see how accurate this prediction is. Okay, and obviously, okay, because we are talking about prediction, right? Okay, the linear regression is about prediction. Okay, so when we talk about prediction, basically obviously, we should talk about machine learning, right? It's machine learning is an umbrella term for a collection of methods, okay, to learn pattern from data, okay, and then use that pattern to predict the future, okay, or to make decision, okay, under uncertainty, okay. So this is a very general definition of machine learning. And if you use that general definition, the machine learning and statistics will, be very kind of intertwined subjects. They have influence to each other actually. The connection become clear if you took a probabilistic perspective. Actually, a lot of machine learning algorithm, okay, its solution, okay, if you try to use a probabilistic approach, okay, the machine learning result, okay, is a special case of probabilistic inference, okay. We actually talk about, remember the mode, okay, in the posterior represents spatial meaning. Remember previously we discussed that, okay. So you will see something similar, later on, okay. So using the machine learning terminology, okay, we can say a regression problem is an example of supervised learning, okay. So under the machine learning framework, we have a regression problem. So we want to learn a mapping from X to Y with Y being a continuous variable, okay. So as I said, we normally say these are features instead of variable, okay. And then, okay, what do we mean by, supervised learning, okay? It means we know the value of the pair, okay? So given X, we know their Y, or given the X value, we know their Y, okay? Sometimes, okay, if we don't know the value Y, okay, then, we are given a bunch of X. What we can do is we can just do the classification, okay? We can, group X with the similar property into clusters, okay, by using certain what we call unsupervised learning, okay. But for supervised learning, okay, you normally has given X, what you want to predict, okay. But of course, that's that is the data set which will be used for training. Once you finish training, you have the model. Then you can use that model. I mean for the unknown y, okay. For given x, you can predict the y. That's like you know. So the supervised or unsupervised learning is talking about training, okay. I mean during the training you have the y or not, okay. So for linear regression model, okay, the core is this formula, yi equal to alpha plus xi beta. This is probably you study this formula like since your junior high school, right, or even earlier. I'm not sure if like if they teach like this thing in elementary school, but I'm pretty sure you have seen this formula in junior high, and obviously at that time probably they don't use variable, right? They probably use just like y equal to a given value plus a given value times x, right? So you have dealt with this formula, you know, at least for like maybe like 10 years, okay? So this is not a new thing, okay? So this is a linear relation between the variable x and the variable y, okay? So parameter beta basically, you know, represent the slope of this straight line, right? Okay? Or you can interpret it as like the change in the variable y per unit change in the variable x, okay? Either way, okay, that's basically like it represents the slope, okay? I think the slope is probably the easier visualization, like understanding of this parameter. And the alpha is the intercept, okay? In Chinese, 截距, right? We all know about that, right? So basically, it's just like you know, when xi is 0, okay, what yi is, right? So now, visually, okay, the intercept is just like I mean, you know, where this straight line, you know, intersect at the y-axis, right? Okay, the value of y, okay, where the intersect this straight line, intersect with like the y-axis. So this is like very easy. Okay, I probably like I shouldn't spend more time on this. Okay, so obviously like you know, if you are into basic statistics, okay, or like if you have studied like machine learning for a little bit, okay, and you should learn the least square fitting, right? Least square fitting. In Chinese we call it 最小平方法. Okay, so this is like you know, it will return, or it's just like for a given set of like xy, given set of xy pairs. Okay, so the least square method return the value of alpha and beta, which will yield the lowest average quadratic error between the observed y and the predicted y. Okay, obviously like for all these pairs, I mean, you draw a line. Okay, that line is impossible to go past all the value, all the point. You just, I mean, you have to find this linear this line such that, okay, it will yield the lowest average quadratic error, okay, between the predicted y and the observed y. Okay, so if you try to, you know, formulate the problem like that, the problem of finding the alpha and the beta will be an optimization problem. Okay, and yeah, this is also one of the example I use in my deep learning class. You know, there's like a matrix solution, okay, to come up with this alpha and beta. Matrix solution is not bad, okay. It's called a normal equation, actually, okay, if I remember correctly, okay. But the time complexity of the normal equation is probably not that great, okay. So another way to do it is like to use, for example, like to use a gradient descent. Okay, you can actually use like a gradient descent. I mean, to find this the best alpha and beta value with the given loss function, which is defined as like the quadratic error. Okay, average quadratic error. Okay, but anyway, like that. Of course, we are not talking about deep learning today. Okay, so yeah, so statistics or if we talk about Bayesian analysis, okay, alternative to optimization is to generate a fully probabilistic model. So when we say probabilistic model, we are talking about Bayesian model. Okay, so thinking probabilistically gives us several advantages. First, we can obtain the best value of alpha and beta together with the estimation of the uncertainty. Okay, we have about the parameters value. So not only we know what the best value will be, but also we know like how certain, how much we should believe that value. Okay, so this is not given if you use that, for example, like normal equation to get the alpha and beta value. You don't know how much you can trust those values, right? But if you use like a probabilistic model, okay, because you have like posterior, right? Once you have posterior, you know like how certain you have for that those values, because you can measure the certainty by using, for example, like the HPD, right? Okay, the wider HPD is, the more uncertain you are to that value. Okay, for example. Okay, and so optimization methods such as like a normal equation require extra work to provide the uncertain information. So this is different. Okay, so additionally, the probabilistic approach. Okay, if you are done using such tool such as PyMC3, will give us flexibility to adapt models to particular problems. Okay, we'll see later. I mean about that. Okay. So in Bayesian model, how do we deal with linear regression? It's like this, because in Bayesian statistics, I mean Bayesian model, I mean we always try to treat like the value as a sample, right? It's sample from like a certain distribution. So you can see, okay, we treat Y to be sampled from a normal distribution, okay, and in this normal distribution, its average is alpha plus beta x, okay? So mu is alpha plus beta x, okay? And with standard deviation sigma, okay? So first, like, okay, because the mu is alpha plus beta x, so it is likely that the Y you sampled will be close to this value, right? Because after all, like in like linear regression, as I said, like the line that you obtained, okay, will not go past all these points. That's impossible, right? Okay, so you will end up having certain error anyway. So Y is actually sampled from this normal distribution. Okay, so as for like your sigma, okay, like this sorry, not sigma, like epsilon. I mean we denote it as epsilon here. So epsilon denote the standard deviation. So what should we do about that? Okay, remember in Bayesian analysis, if you don't know something, put a prior to it. Okay, so we don't know the epsilon, right? We don't know the value of epsilon, we put a prior. Okay, so linear regression model, okay, is the extension of a Gaussian model. Okay, where the mean is not directly estimated but rather computed as a linear function of a predictor variable and some additional parameters. So we do not know the value of alpha, beta, epsilon. So not only epsilon, but also alpha, beta. So we need to set prior distributions for all of them. Okay, remember, anything you do not know the value about, you set a prior to it. So a reasonable genetic choice is like, alpha is normal distribution with mean mu alpha and the standard deviation sigma alpha. And beta is a normal distribution with a mean mu beta and standard deviation sigma beta. And epsilon is like, like half normal. Okay, why we set epsilon to be half normal? Because it has to be positive, right? It has to be positive. I mean, for alpha and beta, we don't know, right? We don't know if it is positive or not. It could be positive, it could be negative, right? So the prior of alpha, okay, even though we don't know the value of alpha, but sometimes, I mean, it depends on the application. I mean, it depends on the problem, okay? So we could use a very flat Gaussian, okay, setting the value sigma alpha to a relatively high value, or to a scale of the data. For example, like said, sigma alpha to be like a 10 or even bigger than that, okay? So that's a possibility, okay? But okay, in general, we do not know where the intercept can be, okay? So its value can vary a lot. For intercept, we really have no idea. I mean, because intercept, I mean, could be positive, could be negative, okay? Even for a given problem, you don't know about that, okay? So for many problems, okay, so its value can, from one domain to another for different domain knowledge. So for many problems, the author of the textbook, okay, has worked on alpha is usually centered around 0 when with sigma alpha, no larger than 10. That's author's experience. It may be wrong. Okay, the author himself, okay, say it may be wrong. But this is just his experience with a smaller subset of problems. Not something easy to transfer to other problems. So it really depends on the problem. Okay, the author admits that, okay, this is not necessarily the case. Okay, that's for alpha. Okay, that's for alpha. Okay, but for the slope, okay, it may be easier to have a general idea, okay, of what to expect than the intercept. Okay, intercept, as I said, like it could be positive, it could be negative, it could range much wider. But for slope, okay, at least sometimes from a problem we can tell, okay, it should be more reasonable to be, for example, positive or negative. For example, like if you are talking about like weight, okay, and the height. I mean, for example, from your height, we can estimate your weight, right? So when the height increase, normally weight should also increase, right? Okay, of course, like for very special case, like that may not be true, but generally speaking, like this is the case, right? The higher a person is, like the heavier that person gets, right? So at least, I mean, for problem like many problems, like we can know like the sign of the slope, okay, as a a priori. So we can we can do a little bit better than just assign a very general situation. We can probably know it must be positive. I mean, if it's negative, it doesn't make sense. Something like that, or it must be negative. Yeah. So for epsilon, we can set sigma epsilon to a large value. Same thing. We don't know that value. For example, 10 times the value for its standard deviation. So we can compute the given data point, their standard deviation, and maybe set it 10 times larger. So this is again like a very flat, like prior for the epsilon. So these are the very vague prior, very flat prior. Guarantee a very small effect on the posterior, so which can be easily overcome by data. In other words, the data will dominate the posterior. That's exactly what we want. Exactly what we want. So for epsilon, actually the author suggests to use, it could be, we could replace half Gaussian with a uniform or half Gaussian distribution. So, but uniform may not be a good idea. Generally not a very good choice. But the Gaussian is, half Gaussian distribution generally work well as a good regularizing prior. So, so later on, in the example, you will see we use the half Gaussian for the prior distribution for the epsilon, and for half Gaussian, so if we want to use a very strong priors, we could use gamma distribution. So it depends on your knowledge to a specific problem. If the problem for this problem, you know like a certain value has it's very likely to be in the range of certain value, then you could set like a Gaussian gamma distribution for that parameter, to make the to create a strong like prior. So default parameterization of the gamma distribution, can be confusing. But the PyMC3 allows us to define it using shape and rate, which are easy to understand. And another even more intuitive way to define the gamma distribution is the mean and the standard deviation. So if you want to see like a gamma distribution, or for example half Gaussian, we just talked about half Gaussian, right? So you want to see the shape of them, so you can check out the PyMC3 documentation. Remember like PyMC3 has a lot of functions that we have covered, but you probably want to check out like a documentation for those functions, to know more arguments that you could use, along with those like functions. So point estimate obtained using least square method will agree with the maximum a posteriori. We call MAP. This abbreviation. So the model of the posterior from Bayesian simple linear regression with flat prior. So as you can see, the point estimate or like the method, the Bayesian, the machine learning method, you use to estimate a certain given value, a point estimate, can be actually approximated by like it can be considered as a special case in Bayesian data analysis. Okay, with flat plier. Okay, so this is like interesting. Actually, okay, Bayesian analysis is even better because, okay, the machine learning method, okay, couldn't incorporate prior, but we are able to incorporate prior, because if you know some problem, okay, you have some, better than flat prior that you could use, okay, for certain parameters, that certainly will make the solution even more plausible. Okay, but in machine learning, it's difficult to incorporate such knowledge, okay, easily. It's difficult. Okay, so this is like a advantage of the Bayesian data analysis. So this is like the Kruschke diagram for linear regression model. So you can see obviously like here we have not broken it into groups. In other words, this is not a hierarchical model yet. We will talk about hierarchical model later. Okay, this is just a very simple linear regression model. So it's a normal distribution, and in this normal distribution, mu is defined as alpha plus x beta. Okay, and this is equal sign. In other words, this mu is a constant variable. Okay, and the epsilon comes from here. It comes from half Cauchy, and the alpha and the beta. Okay, the alpha comes from here, normal distribution. The beta comes from this another normal distribution. So this is the simplest linear regression model we could use in Bayesian data analysis. Okay. So if you want, you can synthesize. You can generate a data set like here. We set random seed and we generate like 100 points. Okay, and these 100 points. Okay, well, I will not go into the detail, but here we just point just point out this number like this. These numbers are not actually these numbers are not purely randomly generated. They are generated somehow like close to this line. We just try to add some randomness, okay, so that when we generate the points, so that these points are not exactly on this line. Okay, but the points are generated like in the sense that if you look at their y value, okay, in other words, you project all these points to the y value statistically, and you draw a kernel function, okay, to show the populations of the y value, you will see that, okay, it is a little bit more concentrated around like a 12. So you can see here it's more concentrated, right? Okay, so it's something like this. So this is the data set that we generated. Okay, this is not a real data set, but we intentionally generate this data set so that, well, it looks like it is linear. This data set, looks like it follows a linear formula somehow. Even if you do not look at this line, this solid line, you can see that, okay, there's like a linear relationship between x and y, right? Hopefully, right? At least like a correlation is high, right? Right, between x and y, the correlation is high. And then, okay, we can build a model and fit this data set. Okay, so, well, So this is very simple one. Basically, like it's just like we try to, convert this model into the program. Okay, so it's like this. Okay, and we generate like 2,000 samples for each chain, and here Q equal to 1,000. What does that mean? It means, remember, like by default we use first 500 to initialize the chain, right? This 2 just means we use the first 1,000 to initialize the chain, certain parameters in a generation. Okay, so that it can generate the result better. Okay, and here, okay, the deterministic variable such as like this you can remember I say like you can put like a mu because it's deterministic. You can put it outside, but if you put it outside, you have to use PM dot deterministic to indicate that this is like a deterministic, mu equal to alpha plus x times beta. Okay, so this deterministic means, okay, it's a deterministic or like a variable that gets computed from these values. And if it's like if the variable is like equal to like a certain distribution, then it's a random variable. Okay, and obviously, if you remember what you saw earlier, you can actually put it here, inside here. So what's the difference between this one and this one? The difference is that, okay, everything every variable that you defined, okay, will be later, recalled by the trace. Okay, so here, if you put it inside here, then okay, in such a case, the variable will still be computed, but not saved in a trace. Okay, so you can put it like here, but it will not be saved. Okay, if you put it like here, you can, the sample, the trace will record, the everything. Okay, so this is the result. Okay, you have your alpha, you have your beta, you have your epsilon. Okay, and but of course, this is not. It's difficult to observe like much from here. Okay, just from the posterior. It will be easier if you look at like from like top. Okay, you see like the joint distribution. Okay, you don't just look at one the marginal distribution, because marginal distribution doesn't help that much in this case. Okay, but if you look from the top to look at like a joint distribution, then what happens that, okay, you will find that alpha and beta are highly correlated, right? Very, very highly correlated. Is it a good thing? Is it a good thing? First, why is this? Second, is this a good thing? We are running out of time today, but let me at least explain why we end up with such a high correlation. Okay, remember, like, okay, when you generate this, okay, eventually, okay, the point will go through the mean of x and y. Okay, we know, like, because, like, the mean of x and y the line will go past that. So yeah, so mean of x and y is a point, right? Okay, mean of x and mean of y. And then, okay, obviously, like in a Bayesian, because it's a distribution, right? So when, how should I say, when one variable change, because it's confined by that linear formula, right? Because we have, even though, sorry, wrong order. Yeah, why? It's like this, right? Okay, so remember I say, like, it will go past the mean of y and x, right? But once you pass that, when you increase the value of y, because it's confined by this formula, right? So when y increase, x gets increased too, right? When y reduce, x gets reduced too, right? Well, it depends on the beta, of course. If beta is negative, when y increase, beta x reduce. When y reduce, beta x increase, right? It depends on the value of beta, the sign of beta. Okay, but anyway, okay. So you can see, because of this linear equation, okay, the x and y are sorry. How should I say? Yeah, I'm talking about alpha beta. Because we are talking about this alpha beta, not x and y. This is alpha beta. Okay, let me correct myself. Okay, so this is so we will go past the mean of x and y, and but when alpha increase, beta has to reduce, right? Okay, same thing, when alpha decrease, beta has to increase in order to go past the same point, right? Okay, because it's confined by this linear equation. Okay, so as a result, okay, you end up having such a very confined correlation. This is not good. Okay, this is actually not normally. Okay, we don't like such a close, such a tight correlation. That's normally not what we are looking for. Okay, yeah, but once, probably, yeah, we only have time to explain why it's like that. The reason we call this a wheel of fortune is because, like, it has to go through the mean, right? So the straight line actually, can only be like a kind of like a, because if this is wheel of fortune, if this is a point of x and average x and y, this is a point. So you can only pass, my bad drawing, sorry. If this is a point, either you pass this or you pass this. So, the line can, can change direction, but it must pass this mean of x and mean of y. Okay, but as I said, okay, because it has to pass this same point. So if you increase alpha, you reduce beta. If you increase beta, if you reduce alpha, you increase beta. Okay, this is the line represented in, the linear line. In your linear regression model. Okay, be very careful. Okay, here we are not looking at the linear regression line. No. This is a joint distribution This is joint probability distribution for alpha and beta. Okay? Okay? This is not that. The line is like the wheel of fortune in the sense that it has to go past that point, the mean of x, the mean of y. But if you change the shape, the slope, the intercept also change accordingly, and which cause like a correlation, close correlation of this joint probability distribution. Okay, I hope I'm conveying this concept. To you, already. Okay, if not, okay, yeah. Well, we are running out of time, so let's stop here. Okay, so next time I will continue to talk about what method we can use to alleviate such issue. Okay. Okay. So we do certain variable manipulation to get rid of this correlation. Okay, but let's talk about that next week. Oh, not next week. The week after next. Okay.